even over here, even if you don't want to speed up, you still have to have the centripetal acceleration because that is what changes the direction. It makes it go, the direction go from up to left to down to right. When you go in a circle, the linear velocity changes direction continuously. The cool part is that the angular velocity doesn't, because in the angular world, as long as it's circulating in a constant direction, we get to call that constant. So even though it's going around and around and around, and its velocity, its linear velocity is continuously bending to stay tangential to that path, on the angular side, we get to call that constant. Because our whole assumption is that you're going in a circle, so we only have to say plus for one way and minus for the other. That's the only option that you can have. Okay? So that's, of course, precisely why this thing right here, we're not going in a constant direction if you talk linearly, but we are going in a constant direction if you talk angularly. And that, of course, is why the acceleration centripetal is not 0, but the angular acceleration is. Okay? So this would be a good opportunity, now that we've done the 3 cases, to remind ourselves that acentripetal and atan are just 2 digestible aspects of the same acceleration. An object really only has 1 acceleration. If we want to break that up into 2 digestible pieces, we can do that. But it might be a good thing to draw in what does the actual acceleration look like. If the acceleration has an inward component and a forward component, then the acceleration as a whole looks like this. So here, the acceleration, I will say it's inward and forward, meaning with the velocity. The acceleration is partly inward to hold the turn. It's partly forward to make you go faster. If you wanted to, you could even talk about the angle between the velocity and acceleration. The angle between the velocity and acceleration is less than 90 degrees. Because again, the acceleration is more with you than not if you're going faster. Likewise, if I were to draw the total acceleration in here, it would look something like this. It has an inward and a backward component. Inward and backward. If you wanted to talk about the angle between the velocity and the entire acceleration, it's more than 90 degrees. And of course, only in the constant speed case can you be sure that the angle between the velocity and acceleration as a whole is exactly 90 degrees. Because of course, atan disappears completely, so acentripetal is the beginning and ending of the story. So if I were to summarize this, let's do a little demo. I'm going to take what is velocity. I used the black marker. Okay, so I'm going to stick this black marker sticking out of my chest. Of course, it's convenient because whichever way I walk, my velocity vector is going to point there, right? So let's specifically do a circle. The acceleration I've done in green. So this is going to be my acceleration vector. If I want to speed up, as behind me, if I want to slow down, it's against me, right? But that's all happening along a line, right? See that? So this, I'm going faster, and this, I'm going slower, and then, of course, I can maintain my speed, okay? So that's linear motion. But now I also need to have an inward component just to hold the turn. So if I just want to maintain my speed, it looks like this. So that this inward acceleration is just holding me in my turn. If I turn it off at that moment, I just go in a straight line, right? I fly out of the turn. Okay? So that's me going in a circle at a constant speed. Now, if I want to go faster, I need a component with my motion. Okay? Like this. If I want to slow down, I need a component against my motion as well. So it's like that. So the angle here is more than 90 as I'm slowing down. If I want to go faster, I have to make it less than 90. And if I want to just maintain my speed, it's equal to 90. Okay? Are there any questions on that? I'm going to stop because I'm getting dizzy. Okay. So it's always need an inward component to hold your turn, and then you may also have a forward or backward component. Any questions on that? Okay, so this has some application to car racing. So let's say you are going in a car. If you don't have a, if you're just racing on a flat track, the force that you get from the ground comes from friction. We learned, of course, that friction has usually some limits. So you have a certain maximum force you can get from the ground, and that means a maximum acceleration. But I can choose how to apply that force and acceleration. So let's say I'm taking a turn. I can choose how to apply that acceleration. Let me draw like a little arc here. This would be potential accelerations. And of course, I haven't drawn the other, I haven't drawn it as a full circle. I've only drawn it with the acceleration vectors all having a component to the left under the assumption I want to make a left turn here. Okay. In fact, if my acceleration as a whole was just like this, I would go faster, but I wouldn't be able to turn, right? And if this was my acceleration, I'd just slow down. So really, I wouldn't want to use this or this if I wanted to make a turn. This, by the way, sometimes if you want to look it up, it's called the circle of friction. It's basically talking about allotment of resources. So you have a total force and a total acceleration, that maximum that you can get from the ground. And from there, you can choose how to spend it. If you spend it here, you're spending it on cornering, which is to say you're using it entirely on centripetal. But of course, if you're doing one of these intermediate things, like this one, if you're using part of it forward, guess what? You've sacrificed on your cornering. Okay? So if you spend a little bit more on a tan, right, to maybe pass somebody, well, if you use a little more to pass somebody, you have a little less available for cornering. Okay? So if you want maximum cornering, what you should do is make sure to lay off the gas pedal and the brake pedal, because you don't want to be using any of your resources on tangentially. You want to use it all for centripetal. Okay? So by definition, if you have more for a tan, you will have less for a centripetal. If there's a total maximum acceleration that you have available, you can choose how to allot your resources. Okay? Now, this is complicated by several different factors, one of which is that if you actually lay on the gas pedal, many cars will actually go higher, more into the ground, have a higher normal force, and it'll actually increase your friction. So I'm trying to take that out of it. So I'm assuming here that we're just talking about resource allocation between cornering and going faster or slower. So safest way to corner is to not be simultaneously trying to speed up or slow down. Okay? Does that make sense? Okay. So next thing, we've gotten our entire toolkit going here. Next thing, I'm just going to try to do an everything but the kitchen sink type of example, which you have several of on your homework. Are there any questions before I do that? Okay, so let's do one final example here. This will close us out for homework 8.
Can you not erase the circle of friction yet?
Sure. Somewhere. here's my example. So I'm going to have a top view of a car. That car is going to be initially going at 20 meters per second. It's going to go around a turn while braking, such that by the time it's finished a half circle, it's only going 5 meters per second. So maybe you're taking a turn and notice there's a traffic jam ahead, so you have to slow down too. Let's say the radius of this circle is 10 meters. And let's talk about that it's a smooth speed decrease. That's, of course, what gives us the license to use our constant acceleration equations. Okay, so if you have a smooth speed change, we can do that. So that's kind of like our code word for constant alpha. And that should be sufficient if we smoothly connect these two speeds along a circle of radius 10 meters, of which we travel half of, it's half of our semicircle. Let me just ask a bunch of questions. So on the linear side, let me ask for some stuff, and the angular side, let me ask some stuff. And really falling in the category of neither, what's the time it takes? So that's not, there's no such thing as rotational time. On the angular side, let me ask for the initial angular velocity, final angular velocity, angular acceleration. And the linear side, let me ask for the magnitude of A tan, A initial, and A final. Okay, so let's do it. So first things first, let me convert everything over to the angular side so we can kind of have a consistent set of variables. I know that at any given moment, I can relate the linear and angular speeds using this equation. So this is true at any time, and in particular, let me use it for the initial moment. So my initial angular speed is my initial angular or linear speed divided by the radius. So 20 meters per second divided by 10 meters. So I'm going 20 meters per second at a radius of 10 meters. So 20 divided by 10, that's 2. And then the meters cancel, so I'm left with just per second. This is where I have my fake unit of radians just thrown in to hold the numerator. So I just throw it in. It's a fake unit, it's not really unit, so I can throw it in whenever there's nothing in the numerator that would otherwise hold the units. So what this is telling me is that if I'm going at 20 meters per second in a circle of radius 10 meters, at that moment I'm also sweeping out 2 radians of angle per second. Okay. Now remember, these equations only relate sizes, so let me go ahead and throw in the direction myself. If I wanted to talk about the vector hat, that's positive, because that's counterclockwise. And similarly, to spare you suspense, the final angular velocity, is that plus or minus? So the final angular velocity is still going the same direction in the angular sense. It's still going counterclockwise. Even though it's completely switched from right to left, as far as the angular side goes, it's constant direction. It's going constant counterclockwise. So still counterclockwise. And then if you divide you should get, what, 5 divided by 10, so that's 0.5. Now it's only covering 0.5 radians of angle per second, because it's slowed down. So those are my initial and final angular velocities. And now that I've gotten everything over to the angular side, I can just go ahead and put in my equations. So I list my 5 variables, no particular order. For reasons that I don't want to get into, we omit the vector hats, but signs go in, signs come out. Okay? So I put in the sines plus 2 plus 0.5. We also know the angular displacement here. What is that? How much angle is covered here? It's a half circle, so that's pi, right? So remember, we have to be in radians. Can't do it in degrees or anything else. Is it plus pi or minus pi? Are we going counterclockwise or clockwise?
Plus pi.
It's plus, right? It's a counterclockwise half circle, so that's why we put in plus pi there. So there's our required 3 things. We can, of course, solve for right away. We can solve for the time, ignoring this. So we pick the equation without the angular acceleration. Which one is that? That's number 4. Or, of course, we are asked for that as well, so we can ignore the time. So the equation that's missing the time is number 3, right? So this is just old hat, same problem-solving strategy, no problem, hopefully. For the, I'll tell you the answers, work them out at home, make sure you can get them. The time is 2.5 seconds. And the angular acceleration comes out to be minus 0.6 radians per second squared. Came out negative, is that okay? Is that an error? No, it better come out negative because we're slowing down. So omega is positive and angular acceleration better be negative. Remember, signs go in, signs come out. Now that it's kind of been through the equation, we might as well remember that this is indeed appropriately signed. So let's take stock here. We've gotten a good way through this. These first 2 are pretty easy because we had their linear counterparts, so we just needed to translate those into angular velocities. These we didn't have, but we solved. And now we're ready to progress, converting back out to the linear side, since we, of course, know everything we need to know. On the angular side, there's nothing left. Right? Are there any questions before I do that? Okay, so next thing, well, ATAN is going to be a cinch because we have its rotational counterpart. So anytime you have the linear version, the angular version, or vice versa, is easy to get. Okay. Here again, remember, when you're doing the linear to angular translation, don't put in the signs. So implied or absolute values. So I go ahead and put in the 10 meters, and then there will be no reason to keep the minus sign here, because it would have no meaning once it punched through to the linear side. So what do we have? 10 times 0.6, that's 6. The units are meters times radians per second squared. This is where the radians, just like we brought it in, we give it the boot because it's a fake unit. We have some something sliding in to hold the units up top. We have the meters sliding into the numerator, so we don't need to write meters radians per second squared. We just write meters per second squared. So that's the tangential acceleration. If the angular acceleration is constant, so will this. So if we want to change our speed smoothly, that's going to have to be the amount of acceleration that always acts against the motion. I can sketch it into my original diagram. It looks like this. 6 meters per second squared working against the motion there. And 6 meters per second squared working against the motion there. Notice, by the way, if it's going to keep up, once the velocity switches direction, it needs to switch direction, so it's always working against you. That's the only way you're going to keep slowing down, is if you have something working against you. So now we have a tan. However, you may be surprised seeing A initial and A final, because I just said that the tangential acceleration is the same. The difference is going to come in the centripetal. The centripetal acceleration is not the same, because it turns out you have different needs of going in the circle going at different speeds. Let me remind you that how much acceleration you need to hold the turn is dependent on the speed itself. So A centripetal equals v squared over r. So you can see there's a strong dependence between how fast you're going and how much acceleration you need. If you're going faster, you need a lot more. If you're going slower, you need a lot less. So if I sketch this into the diagram, it kind of looks like this. A centripetal is very big at first and much smaller later. You're going slower, you need less of it. So here, even though we have a smooth speed decrease, our acceleration is quite complicated, because while the needs of the speed change are not so challenging, we're going to need a different amount of acceleration to hold the turn at different points along the motion, because the speed is changing. So let's work it out. So A centripetal initial is v initial squared over r. That's how much acceleration I need at first, at the initial moment, to hold the turn. And I should mention, by the way, that if you plug in v initial is r omega initial, there's a useful alternative formula for how much centripetal acceleration you need in terms of angular speed instead of linear speed. So I guess I can add that here to my master chart. Instead of saying v squared over r, I could also say r omega squared. That's just an alternative expression. So let's work out what that is. If you put in, you should get, what is that? 2 squared times 10, that's 40. That's how much acceleration you need to hold the turn to start with. And then similarly, if you want to work it out at the end, you'll find that it's only, I had it written down. Well, let's see. Let's work it out. So 0.5, what is it? 5 squared divided by 10, 2.5. They're all over here, so that would be, I guess if I use this, 0.5 squared divided by 10. Oh, sorry, 0.5 squared times 10, right? So this is 0.5 squared times 10. And the first one was 2 squared times 10. So I can go ahead and put those in here. My needs for holding the turn are quite large at first, and my needs for holding the turn are very minimal at the end. So while I have required a speed change to be smooth, that's why a tan is constant. A centripetal is evolving. So what I was asked for, in fact, was not centripetal or tangential specifically. I was just asked for the total acceleration initially and finally, so I need to reassemble. So this is just vector components being reassembled, just like earlier on in the class. This here, how do I get the hypotenuse again? Pythagorean theorem. Okay. If you do that, Pythagorean theorem, that comes out to be 40.4 meters per second squared.